A civilian nuclear power station is a static concrete structure built on stable bedrock. A naval nuclear reactor is a mobile propulsion system subjected to the violent pitch, roll, and hydrostatic forces of the deep ocean. To function in this environment, a submarine reactor must meet three unforgiving physical constraints. It must generate immense heat entirely without atmospheric oxygen. Its pressure boundaries must withstand the crushing weight of deep submergence, and it must operate continuously for up to 40 years without a single midlife refueling. Subjecting a nuclear core to extreme thermal transients, constant vibration, and nearby explosive combat shock creates an incredibly hostile operating environment. Yet, the United States Naval Nuclear Propulsion Program has operated for over 75 years, accumulating more than 7,600 reactor years without a single severe accident. This chart compares the safety records of the military and civilian sectors. While the U.S. commercial sector is heavily regulated and has logged over 4,000 cumulative reactor years, its history includes severe accidents like 3 Mile Island. In contrast, the U.S. Navy operates 97 active reactors, a fleet size comparable to the civilian sector, with an accident-free record that has stood since 1948. Operating these plants requires an engineering discipline focused entirely on survival in a high-pressure maritime theater, rather than the steady-state efficiency of the civilian power grid. Translating these extreme physics into physical hardware relies on a single corporate entity. BWX Technologies is the only commercial heavy nuclear component manufacturer in North America capable of fabricating these highly specialized reactors. The scale of this dependency is massive. Driven by the simultaneous production of the Virginia and Columbia-class submarines, alongside the Ford-class aircraft carriers, BWXT has executed a multi-billion-dollar capital expansion, securing over $4.7 billion in recent pricing agreements to scale its production capacity. The barriers to entry for this industry are functionally insurmountable. Securing the necessary Category 1 Nuclear Regulatory Commission licenses to handle highly enriched uranium, combined with the required multi-billion-dollar heavy machining infrastructure, prevents any near-term disruption to this supply chain. This unique industrial architecture purposefully isolates the Navy's strategic supply chain. By maintaining a highly secure, vertically integrated network, the program shields its reactor production from the cost-cutting pressures and schedule optimizations that dominate standard commercial markets. A commercial nuclear power plant is refueled every 18 to 24 months. Because the fuel is cycled out quickly, civilian reactors utilize low-enriched uranium, or LEU, which contains less than 5% of the fissile uranium-235 isotope. To keep a submarine operational for up to 40 years without opening the reactor, the fuel matrix must contain a massive energy reservoir. Naval reactors utilize highly enriched uranium, or HEU. This material is enriched to over 90% uranium-235, providing an incredibly dense concentration of fissile isotopes within a tight physical volume. Loading 4 decades worth of highly enriched fuel into a compact core creates a severe mechanical challenge known as excess reactivity. If left unchecked at the moment the reactor is first turned on, this massive reserve of fissile material would trigger a catastrophic prompt critical power excursion. Engineers solve this by embedding precisely calibrated burnable poisons directly into the fuel matrix. These are neutron-absorbing materials that physically suppress the initial excess reactivity. As the uranium depletes, the poisons burn away at a perfectly matched rate, maintaining stable criticality for the life of the ship. The fabrication of this exactingly calibrated HEU fuel is executed at BWXT's heavily guarded Nuclear Fuel Services facility in Erwin, Tennessee. Mastering this fuel matrix eliminates the need for mid-life refueling overhauls. This removes a massive industrial bottleneck, keeping the submarine deployed in the ocean rather than cut open in a dry dock. In anti-submarine warfare, survival relies on acoustic stealth. A nuclear vessel must evade advanced passive sonar arrays that listen for the slightest mechanical vibration. In a standard pressurized water reactor, massive mechanical pumps are required to force coolant through the dense fuel rods to remove the intense heat of fission. However, these pumps generate low-frequency tonal noise that can be detected by enemy sensors. This diagram illustrates the principle of natural circulation. This thermohydraulic engineering solution exploits thermal convection, allowing the reactor to circulate water through the core entirely without the use of mechanical pumps. Naval architects achieve this by strictly offsetting the heat source and the heat sink. The reactor core is positioned at the lowest possible point within the submarine's hull, while the massive steam generators are elevated as high as physically possible. As the primary water surrounding the fuel rods is heated, its density decreases. This hotter, lighter fluid naturally rises through the piping to the elevated steam generator. Here, it transfers its heat, cools down, becomes denser, and naturally sinks back into the core, creating a continuous, silent convection loop. This silent thermosiphon effect provides enough thermal transfer for the submarine to conduct intelligence patrols at loitering speeds. When high-speed transit or combat evasion is required, the primary coolant pumps are engaged, rapidly transitioning the plant to forced circulation for maximum tactical power. Natural circulation marries high-density nuclear physics with fluid dynamics to render the submarine acoustically invisible during its most sensitive mission phases. The primary coolant loop and the reactor pressure vessel must simultaneously endure crushing hydrostatic depth pressure, extreme radiation flux, and rapid thermal cycling. Beyond environmental pressures, the reactor must survive kinetic military threats. Under the MIL SS 901D heavyweight shock standard, equipment must withstand the shockwaves generated by near-miss depth charges or modern torpedoes. To survive these explosive impacts without fracturing, BWXT forges the pressure vessel from specialized vacuum-degassed low-alloy steels. These thick-section forgings undergo vacuum degassing during the molten phase to remove hydrogen, ensuring the homogeneity of the metal under extreme stress. The metallurgy is strictly controlled to minimize trace impurities like copper and phosphorus. If these elements are present, the constant bombardment of neutrons will cause the steel's crystal lattice to become brittle over the ship's 40-year lifespan. Inside the high-temperature primary loop, materials face the threat of stress corrosion cracking. The combination of tensile stress and a highly pressurized aqueous environment can cause rapid failures in standard metals. To combat this, the Navy transitioned to Alloy 690, a specialized nickel-based superalloy. By doubling the chromium content to roughly 30%, Alloy 690 forms a robust passive oxide layer that is essentially immune to stress corrosion cracking in primary water. Strict metallurgical standards ensure the reactor's primary pressure boundary can endure both the long-term corrosive effects of high-temperature water and the immediate concussive force of underwater explosions. This chart contrasts two distinct safety paradigms. While commercial nuclear and aerospace industries often rely on probabilistic risk assessments to manage acceptable flaw sizes, the naval nuclear domain rejects this approach in favor of a deterministic model. Instead, the Navy enforces rigorous non-destructive evaluation standards dictated by NAVSEA. These requirements establish a zero-defect workmanship philosophy, demanding that every component is fabricated to the absolute limits of mechanical perfection. This diagram maps the application of non-destructive evaluation across a reactor plant. Technicians utilize 100% volumetric inspection, employing high-frequency ultrasonic testing and radiographic testing to interrogate the deep structural boundaries of heavy-walled pressure vessel welds. Naval inspectors are searching for microscopic voids or gas pockets deep within the metal. Under the static loads of a commercial plant, these might be deemed acceptable. But in a submarine, they act as internal stress concentrators that could succumb to the cyclic fatigue of rapid deep-sea depressurization over a 40-year cycle. Any identified microscopic flaw mandates immediate surgical excavation, rigorous rewelding procedures, and thorough reinspection. The short-term cost of repair and schedule delays are never weighed against the structural integrity of the primary pressure boundary. BWXT's rigorous adherence to these NQA-1 quality assurance standards ensures that the safety margins calculated by physicists are accurately translated into physical hardware. Maintaining this degree of physical and metallurgical perfection requires a bespoke regulatory architecture. The program is shielded from conventional defense acquisition bureaucracies, cost-cutting measures, and standard military oversight. This chart outlines the unique dual-hat framework governing the Director of Naval Reactors. By holding concurrent authority within both the Department of the Navy and the Department of Energy, the Director exercises absolute, unappealable technical control over every phase of a reactor's life cycle. This operational independence is reinforced by a severe security ecosystem. Under the Atomic Energy Act, technical data regarding naval reactor design and fuel manufacturing falls under the doctrine of restricted data, meaning the information is legally classified from the exact moment of its inception. Because they handle this restricted data alongside strategic special nuclear material, personnel on the BWXT manufacturing floor must secure exhaustive Department of Energy Q clearances. This establishes a highly restrictive baseline for anyone working directly with the reactor core. This legal and security fortress guarantees that technical safety parameters remain inviolable. They can never be overruled by fleet commanders requesting a tactical advantage, shipyard managers facing a deadline, or shifts in political cycles. This centralized technical control originates with the standards established by Admiral Hyman G. Rickover during the development of the USS Nautilus in the 1950s. This graphic details the 4 pillars of high reliability that define the program's organizational psychology. It demands complete personal responsibility and rigid technical discipline over the standard military practice of decentralized risk management. The integration of extreme physics, heavy manufacturing, and unrelenting human discipline yields a single, undeniable metric: over 7,600 reactor years without a single severe accident. The U.S. Naval Nuclear Propulsion Program safety record is the direct output of these integrated engineering standards, centralized oversight, and an institutionalized culture of absolute personal responsibility.